In the last video, I introduced you to the big decimal class and the different ways to construct a big decimal, as well as the problems you might run into when constructing a big decimal instance. One of the advantages to using big decimal is that you get to decide how to round a number and what scale you want to use. I'll be using the big decimal project from the last video and the code in the main class's main method. I'll delete this commented out code before we begin. Going back to my last for loop, I'm going to change the scale on each of the big decimal instances in my loop. Let's say I only want 2 decimal places, that these numbers represent financial numbers, so I want a scale of 2 in all cases. Big decimal comes with a method called setScale, so I'll include that after the printf statement in the loop. I'll copy the printf statement and paste a copy below to see what this does to my numbers. IntelliJ is trying to get my attention, but I'm going to ignore it for the moment and run this code. As you can see, I got an exception, java.lang.arithmetic exception, rounding necessary. By saying I want to scale, I need to tell Java how I want numbers that have a bigger scale than 2 to be rounded. In this case, when I specify nothing, Java tries to use its default rounding, which is not to round at all, but obviously in the case of this first number, the least significant digit 6 won't just be dropped. If I change the number from 15.456 to 15.450, let's see what happens with that change. Running this code. I get a little further, and now I get the exception on the 10,000 number. I'll undo that last change. There are cases where you probably know that it's safe not to specify a rounding mode, but in most cases you'll likely pick one. These modes are stored on an enum called rounding mode. I'll start typing rounding mode, adding a second argument to the setScale method call. Right away you can see some of the options there. There's down and half up. There's also ceiling, floor, half down, half even, and up. There's also unnecessary, which you might want to use, just to let people know that's what you intended, rather than calling this method without a rounding mode. I need to pick one to get my code to work. This enum is also in the java.math package, so let me just bring the API for that up here. The documentation provides a very useful table of examples and what will happen if you use any of these modes. I won't go through all of these, but you should try to test these out on your own when you get a chance. I'm going to use half up, which is pretty normal in financial applications, meaning that if anything that is 5 or higher in the insignificant digit will be rounded up. Now if I run this, my code runs, but I'm not really seeing anything changed in the output. I shouldn't have ignored IntelliJ. It's still warning me I've got a problem with this call to setScale. Big decimal is immutable, so when I call setScale, it's not going to change my instance. Instead, it returns a new instance of big decimal set to this new scale and values rounded as specified. To get around this, I'll just reassign my BD variable and assign it the output from that method. It's really important to remember that almost every method you use on big decimal will need to be assigned to some variable. If I run that, I can see the before and after. 15.456 was changed to 15.46. The unscaled value only has 4 digits now. The scale is 2 as I specified, and the precision is now 4. The number 8 has an unscaled value of 800. The number 10,000.000001 no longer has that trailing insignificant digit, so its precision went from 11 to 7. 0.123 just became 0.12. I'll change that number to 0.125 in my array. I will run that again. And there I can see very clearly that the rounding half up mode took my number 0.125 up to 0.13 because the digit it was rounding on was a 5. Okay, now let's look at how you do math with big decimals. Let's again just go to the API and look at some of the methods on this class. So I'll browse to the method summary of this class. These methods are going to feel a bit reminiscent of the math class, with methods like absolute value, add, divide, multiply, so the usual simple calculator methods. Each method returns a big decimal and usually takes a big decimal as an argument. Many of these methods have an overloaded version that takes a math context. So what is a math context exactly? I'll click on that and bring that class up in the API. Here it says this class describes certain rules for numerical operators. And below that statement, you can see that you can specify the precision to be used and also the rounding mode. Instead of being applied to the values, these are applied to the result of the operation. Let's see what this means in some code. I'll set up code similar to the life insurance example I used in the previous video. First, I'll have a variable for the insurance payout amount, which I said was 100 million. I'll call this variable policy payout and make that a new big decimal. I'll pass it the string, which matches the numeric literal I used on line 12. I'll copy the last printf statement at the end of the for loop and paste that at the end of my method. I'll change BD to policy payout there. I'll make sure this all fits on the screen by adding a new line after scale. Running this code though, I get an error. Like the double wrapper, if you create a big decimal with a string, you can't use numeric literal features like underscores or suffixes like L or F. I also can't use commas in this string. I'll remove those underscores and try again. Now my code runs and I can see that I get 100 million there with a scale of 0 and precision of 9. I'm going to change my string again. This time, I'm going to format my string literal like I would for a financial number that included some part of a dollar. When I run this, what I want you to see is that I can control the scale by the way I define my string literal. In this case, my scale is now 2 and precision is 11. I can also use E notation in my string literal, and I'll show you that next. Because my number is 100 million, I'll use 100E6 because it's easier to remember that 6 stands for a million, at least for me. If I run this, I want you to see what I have now, a negative scale, minus 6, which corresponds negatively to E6. A negative scale doesn't mean the number is purely fractional, which you might imagine at first. On the contrary, it is simplifying having to include, in this case, all the places less significant than a million. In fact, when you now apply rounding to a number with a negative scale, you'd be rounding in the millions. Since this is not what we want, I'll undo that last change. Next, I want my percentage value based on my beneficiaries, so I'll set up another big decimal variable and call that %. Big decimal provides some static big decimal values for us, so we don't have to create the most common values. These are big decimal.0, big decimal.1, and big decimal.10. I'm going to use big decimal.1 and call divide on that, passing it a new instance of big decimal that I'll get by using value of and passing it my integer beneficiaries. It's true the math isn't pretty, but the peace of mind it buys will have you looking seriously at coding things this way at times. I will print this big decimal value out. If I run this, I get an exception, non-terminating decimal expansion, no exact representable decimal result. As we already know, 1/3 will repeat forever. In this case, I haven't specified how I want to round this infinitely repeating decimal. I'll use the overloaded version of divide, and now I'll pass a math context. I'll start by trying out some that are available on this class. I'll add a comma after the first closing parentheses and include a new line. I'll pass in mathcontext.unlimited as my second argument to the divide method. Running this code, I get the same exception. Mathcontext.unlimited is the default math context used when you don't specify anything, and in this case it's not good enough. I have to round this number somehow. I have several other preset options to choose from, so next I'll try decimal 32. This code now runs and I get a representation for my percentage that has a scale of 7 digits after the decimal, so much like a float. I'll try decimal 64 next, and running that. I now have 16 digits after the decimal. I'll switch to decimal 128 and see what I get. This setting gives me a precision of 34 digits, the 0 before the decimal is not counted. But what if I needed even more precision than that? Well, I can always create my own math context instance and specify exactly how precise I want it and how I want it rounded. Notice that each of these numbers ended in 3. But let's say that for whatever reason I want to round up the last digit and I want a precision of 60. I'll pass a new math context with the value 60 and rounding mode dot up in that constructor. if I run this. I get an even more precise representation of 1/3 than the other three standards. Big Decimal is said to have arbitrary precision because you, the developer, get to decide what precision you need and want to use in your math operations. Let's now get the check amount for each beneficiary using more Big Decimal math. I'll create another variable, check amount, and assign that the result of calling policy payout dot multiply, passing it %. In this case, I won't pass a math context. I'll print the result after that, formatted to 2 decimal places. If I run this code, I might feel pretty good about the results. I get the expected check amount, which is 33 million, etc. But is this really the value? I'm going to copy the printf statement directly below the policy payout declaration and paste a copy at the end of the main method. I'll change policy payout to check amount in every case there, so in 4 places. If I run this, the results tell me something quite different. My check amount has a precision of 70 and a scale of 62. If I'm not careful, I'm going to lose a penny. When you do Big Decimal math, the scale is determined by the operation you're using. For multiplication, the scale is the 2 operand scales added together. My policy payout had a scale of 2. My percent variable had 60, so my scale is 62. For the rest of my math to work as expected, I'm going to need to set the scale on this result to 2 to represent a partial dollar amount. I'll reassign check amount to the result of calling set scale on that instance, passing it 2 as the scale, and rounding mode dot half up. If I run this, I can see that my check amount has the expected scale, which matches the policy payout. Finally, I want to get the total amount of the checks, so I'll take the check amount. I'll multiply that by the number of beneficiaries, again creating a Big Decimal from that with the value of method. I'll print out that amount in a formatted string. I'll subtract that from the policy payout. Running this code, I can see that the combined amount is a penny short of 100 million. And that's the amount I get as remaining. This is good news. I haven't lost a penny in the math. For good measure, I'll copy this printf statement just above the total checks amount declaration and paste a copy at the end of the method. I'll change all instances of check amount to total checks amount. I'll run that code. What I want you to see here is that the scale is still 2. I multiplied a 0 scale number, beneficiaries, to a scale 2 number, which gives me a scale 2 number as a result. Okay, so I'm going to bring this discussion about Big Decimal to a close. You can see there's a lot of functionality on this class, and it's important to understand how it works. You'll want to consider using Big Decimal in the event you're working with applications that need access to very precise big numbers, or if you're working with financial applications. I'll be talking about another class called Currency when I get to localization and internationalization, which can be used to pick the proper scale for your currencies. For now though, I'll end this video here. Practically every application you write in Java is likely to have some kind of requirement that deals with dates or time. That's what I want to cover next, so I'll see you in that next video.